hold on. Sorry. Yeah. Yeah. All right. Yeah. Yeah. I lose a lot of things. Yeah. Yeah. I forgot to turn on. Sorry. Now, Zoom side students. Now you can hear, right? Zoom side students. Yeah. I think I just turn on my remote microphone. Yeah. All right. Yeah. Yes. Oh, good. Okay. Yeah. Thank you for your feedback. Yeah. Yeah. Sorry. Yeah. So then, 10 minutes. We lost 10 minutes. Yeah. All right. Yeah. So here, if we do subtraction between these two fractions, you can see we need to divide by omega squared to make the same. Divided by omega squared. Because numerator omega squared, we need to cancel out. Numerator omega squared. All right? Then, by the linearity property, take the constant out, linearity property, so we get this expression. Then, apply the basic formula, basic Laplace transform, inverse transform formula. That's from there. See? That's from that formula. This one from sine. Remember, sine formula. So you see the final result, the same as that function. The same. Okay? So you have different ways to find Laplace or inverse Laplace transform. It depends on how do you understand the structure of the given function. You have several ways to understand the structure. Here, we use this way to understand the structure. So you can see this way is simpler than the previous way. A little simpler than the previous way. Yeah. Yeah. Try to understand these simple algebra techniques. The algebra techniques. Okay? Yeah. All right. C.5, solve IVP by Laplace transform. Yeah. Now, IVP, so you can see, also we only need to do algebraic operations. That's good enough. Yeah. All right. Yeah. Let's look at the example. Yeah. General. Yeah. First, let us solve this general second order ODE initial value problem. Yeah. Let's apply Laplace transform. Yeah. We just use these two formulas. Yeah. All right. Yeah, so because Laplace transform, it's a linear operation, so we can apply term by term by the linearity property, term by term. Yeah. Okay, yeah. So you can see, this simple form. All right. Yeah. Laplace transform of little r, suppose we can calculate. Yeah, we can find it. This capital RS, that's the Laplace transform of that function. We treat as a known function. Here, if little r function is known, we assume we can calculate its Laplace transform. So capital R function also known. Now, we can find it. All right. So then we need to find Laplace transform of y function. Our solution, y function. The first term, we apply this second derivative formula. S squared Laplace transform of y minus initial value k0, y of 0, that's k0 times little s. Second initial value condition k1. Okay, that's the double prime term. Single prime term, A, we apply the first derivative formula, S times Laplace transform, and only use the first initial condition here. Okay? Yeah. So straightforward. Yeah. So we plug in, in a straightforward way. Yeah. This is a algebraic equation. Question.
So the R2 function, if we know what that is, then we automatically know what RS is?
Yes. Yeah. After computation. So here the question becomes how to calculate Laplace transform of a function. Yeah. So here, actually your question makes sense because some functions, it could be very hard to calculate Laplace transform, right? Yeah. Even impossible because it's not all function you can calculate. Some function it's too hard. Yeah. But here, how about we assume the functions that we deal with, we can calculate, not that hard. Because here we consider real-world engineering problems. Those functions, not too complicated. Okay? Real-world engineering, E function, polynomial function, sine, cosine, basically those functions. Then we don't worry about that, right? Yeah. Real-world engineering problems, yeah. So in that way, we don't worry. Yeah. So we can calculate. But if you talk about some, ridiculous hard question, hard function, then, we cannot. We cannot calculate. Yeah. That's true. We cannot. Yeah. All right. Yeah. So now, to solve this algebraic equation, so then usually people find a simplified way, use capital Y to represent Laplace transform of its little y version. Yeah. Just like we use capital F before. Yeah. Here we use capital Y. Just like we use capital R for Laplace transform of little r. Yeah. So capital Y. Yeah. Then, combine its coefficient, the right-hand side, all the S terms. Yeah. You do division. That is the Laplace transform of your solution function. Yeah. Yeah. It looks a little complicated, but you have the Laplace transform of the solution function. Then you just take inverse Laplace transform, you find the solution. Okay? Yeah. Yeah. Solution, inverse Laplace transform of that capital Y. Yeah. So you solve that ODE problem. See? Yeah. So you can compare with our old way. So our old way, we need to find the general solution, right? Particular solution. Then we need to plug in the initial conditions to determine two C constant, right? Yeah. Here you can see, it's a good improvement, right? Yeah. Good improvement. All right. Yeah. Next, let's solve a concrete one. Yeah. Not a, abstract, generic one. Yeah. Concrete. Initial value problem, the basic Laplace step. Yeah, this time let's solve y double prime minus y equals t with these two initial conditions. Yeah. So very simple. Yeah. All the way we need to find the characteristic equation, right? Then the general solution. Then from general solution, then we need to also determine the particular solution, right? That's always. So then constant C1, C2, right? Here, let's try Laplace transform. We want to see how powerful it is. Yeah. All right, let's look at these two formulas again. Yeah. But the first derivative formula we do not need to use because that derivative term is not there, right? Yeah. So the first term we do not use. We just use the second formula. Second, S squared times capital Y, S times the first initial condition minus second initial condition, then capital Y from the Laplace transform of that little y. You see? Then Laplace transform of t, that's our basic formula, 1 over s squared. That's our basic formula. Okay? Yeah. So we use it a few times. Yeah. All right. Simplification. This simplification, I think it's easy for you, right? Yeah. So on your scratch paper, you work a little bit, yeah. Change some order, yeah. You can get that expression. Then, inverse Laplace transform, term by term. Okay. You do inverse Laplace transform for each term. Okay. Then you need to use some of our basic formulas. Yeah. Here I may copy the basic formulas here. Okay. One is inverse 1 over s minus a. Yeah. S minus 1. So you get this function. Inverse Laplace transform. Second, formula number 10, hyperbolic sine function, a over s squared minus a squared. Here, a equals 1. Okay? A over s squared minus a squared. Yeah. Hyperbolic sine function. Okay? Yeah. All right. Then the third, 1 over s squared, yeah, inverse Laplace transform, so you can get a right final solution. How about that? How simple it is. Now, think about if you compare our, old way, our chapter 2, our old way. You can see after you practice, especially after you get familiar with all these basic formulas, yeah, you can put a table aside. Yeah, just the one table. Okay, yeah, on our textbook we have one page, containing that table. You put it aside. Yeah. Then you do calculation like this. Think about how much faster you can do comparing with the old method. I estimate you probably use 1/5 of the time. Is that a fair estimate? 1/5 of the time of the old way. Right? Yeah. So think about that. All right? Yeah. So this method, so good. Yeah. All right. Next. Yeah. Still write down. Yeah. All right. Yeah. Okay. Yeah. So you can look at my note file, PPT file. Comparison with the usual method. Solve the initial value problem. Another one. Yeah, this time. All right. Yeah. This one, you can see the method pretty much the same. Yeah. So here you can see, yeah, our old way. When we solve ODE using we need to identify different types, right? Think about homogeneous, non-homogeneous, right? Also so several different types. Characteristic equation. There are 3 cases for characteristic equation, right? Yeah. So when you solve, you need to consider so many factors. Here, it's like one unified way. You can solve all those questions in one way all the time. Okay? Yeah. All right. Still, these 2 formulas. Yeah. So plug in. Yeah. L double Y double prime. Apply that. Yeah. So we use, capital Y. Yeah. Replace Laplace transform. Yeah. Initial values given. Yeah. Second, that formula. All right. Yeah. So let us, plug in into the original formula, Laplace transform. Yeah. Original. So we get that expression. Algebraic equation. Yeah. Solve for capital Y. Yeah. So we can easily find capital Y. All right. So capital Y equals this expression. Yeah. The next question, we need to decompose this fractional expression. We need to decompose it now to make it fit some of the structures of our basic formulas. Yeah, we have a few basic formulas, but which one to use? So we need to, do some preparation work. Yeah. All right. So here, look at the denominator. Denominator, we want to make squares. S squared plus S. We want to make squares here. Okay? S squared plus S. All right. S squared plus S. These two terms, then plus 1/4, then it's a complete square, right? S squared plus S plus 1/4. That's, if you add these three terms, that's S plus 1/2 squared. You need to see the structure. You need to see the structure. That's the basic operation. We make complete squares in this way. Yeah. All right. So there, look at this. Our basic formula number 11, denominator S minus A parenthesis square plus omega square. Yeah. Here, it's plus, minus A. Yeah. All right. Yeah. So there, sine number 12, that structure, numerator omega, numerator constant. So here, numerator you have S. Yeah. Numerator we have S. Okay. All right. Then, look at the split I made here. Okay, the split. All right. All right, split 1/2. Yeah, because the numerator we need this 1/2 inside the bracket square. Yeah, and the remaining number. Denominator. Numerator. Yeah, we need to make this same structure, okay, 1/2. The other 1/2, multiply 0.16, you get 0.08. That's the decomposition we need. Yeah. Yeah, that's the decomposition. Okay? All right. After that, now we can calculate inverse Laplace transform of capital Y. Right? Inverse two fractions. Inverse of the first fraction. Okay? And inverse, we take the constant part out, inverse of the second fraction. Okay? Yeah. Yeah. And then we make up that omega. We know that omega, root of 35/4. That's the omega, root of 35/4. Okay? Yeah. So, but we need to balance it. After we put omega at the numerator, we need to divide it by that omega in front of the inverse Laplace transform. Okay? So we change the coefficient. Yeah. All right. So these two, then we apply the first basic formula or formula number 11, with A equals -1/2. A equals -1/2. Omega, here, omega root of 35/4. So we can write the final solution here. Final solution. Common factor, we factor that e to the -t/2 out. Common factor, that constant 0.16 out. Inside parenthesis, the first big parenthesis cosine omega t. Cosine omega t, all right? Second, yeah, so because this factor out. This one, root 35 over 35, yeah, times sine omega t. Yeah. Sine omega t. Yeah. This root 35 over 35, it's not that, yeah, because if you use 1 over root 35, it's fine. Yeah. It's not that important. Yeah. Not that important. Yeah. Yeah. Just if we put our root numbers at the numerator, it looks a little better than at the denominator. Yeah. But that step is not very important. Yeah. All right. That's the final solution. Yeah. Yeah. Although the computation, you need to do some work. Yeah. You need to do some work. Yeah. But you can see, yeah, definitely it's a powerful tool. Yeah. It's a powerful tool. Okay? Yeah. Completely new way. Yeah. Yeah. Very valuable. Yeah. That's a Laplace transform. Very valuable. Okay? Yeah. Especially for engineering students. Extremely important. Yeah. Okay? All right. Yeah. So that's someone. Let's look at a few more examples. Yeah. Shifted data problem. Yeah, this is our last example. Shifted. Yeah, this one, there is some conversion step. Yeah, so let me slow down a little bit. Yeah, otherwise it's hard to follow. Because you need to switch. Something like, do you remember we did before? We switch coordinate system, right? We do rotation, we switch coordinate system. It's hard to follow, right? Yeah. Here, there is a similar thing we need to do. We need to switch coordinate system. Okay? Yeah. But it's not rotation. It's a translation. It's translation change of the coordinate system. Yeah. The last time is a rotation. Yeah. It's pretty hard. Yeah. Here, we need to do another, although we do not say coordinate system change explicitly, but actually, the basic operations we do pretty much like that. Yeah. All right, so let me show you the question. Yeah. The question, you see that ordinary IVP problem, ordinary, but only at one place it's different. Yeah. Yeah. Everything else looks the same, but there is only one place, special place, it looks different. Then it causes those problems. Let's look at the question. Yeah, this is not special, right? Laplace transform, you can do it without any problem. But the special part is initial value. We have the initial value at pi over 4. It's not 0. If it's at 0, we can do easily. But here, initial value occurs at pi over 4, non-zero point. Why it is so different? Why the initial point not at 0 so different? Yeah. The reason is simple. Look at our basic formula. In this formula, we need to use the function value at 0, right? If the function value given at a non-zero point, can you apply this formula? You cannot apply this formula, right? That's the reason, okay? That's the reason we need to shift it. So look at the title of the shift data problem. So we need to do a shifting operation to make the coordinate system start at 0, not start at pi over 4. Okay? Yeah. So we want to write a new function that for this new function, initial value occurs at 0, not at pi over 4. That's the basic idea we use to solve this one. Okay? So we need to do some transform, simple transform, okay? Yeah, to fix that initial value problem. Then we can use Laplace transform to solve it, right? Yeah, so that's the relatively hard part. Yeah. All right, so let me try to complete within 10 minutes. Okay. All right. Yeah, here I define a special function, y tilde of t function. Yeah. The function related to y closely, but slightly different. So I use the symbol tilde, okay? Slightly different, yeah. Can I define a function y tilde of t equals original y of t plus pi over 4? I can define it in that way, right? Yeah. Nothing wrong. I just introduce a new function, okay? But you can compare new function, old function. The difference is pi over 4 shift. Pi over 4 shift. That difference. With that shift, an adjustment, you make the initial value occurs at 0. How about that? Initial value occurs at 0. Right? So you fix that problem. Question.
Would we always be given, for this type of problem, would we always be given that y of an initial value and not just like the y prime and then
Yeah. Yeah. What's your question?
Would we always be given that, the first one? Always be given the flat y values, that way we can actually do the shift and
Yeah.
not just the y prime.
Second order, we needed these two. First order, we only need 1. Second order, we need 2. Third order, we need 3, and so on. Yeah. Here, second order. Yeah. Another thing is initial value. These 2 points must be the same. Otherwise, useless. Okay. So you have to have 2 conditions given at the same point. Yeah. Another. Yeah. Yeah. 2 here. All right. Yeah. Otherwise, not solvable, okay? Not enough information. We cannot determine the solution. Yeah. All right. Yeah. So after we define a new function, you can see the initial values will be adjusted to be right for application of our basic formulas. Yeah. All right. Yeah. All right. So there, y prime, you have the same relationship, double prime, yeah, okay, yeah. Then initial condition, y tilde of 0, you plug in t equals 0, that's pi over 2, okay. Y tilde prime of 0, you plug in t equals 0, that's the y prime of pi over 4, 2 minus root 2. See, if you look at the, after we do the conversion, the ODE with respect to y tilde function, you will see initial values are right for the given formula, right? We can apply. Yeah. So that's the key step. Yeah. Other than that, we Laplace transform the same as before. Okay? But we need to do this key step. Okay? Key step. In your mind, you need to follow. Okay? You need to, understand why we can do it in that way. Okay? All right. Yeah. Now, this is the original ODE. Can we convert it to the ODE for tilde? Y tilde? Right? Yeah. All right. So if we let t equals t tilde plus pi over 4. Yeah. Yeah. All right. Yeah, because here our goal, we want to write the given ODE for the tilde version, y tilde version of ODE. So we can solve. Okay? So to do that, we replace little t by t tilde plus pi over 4. Yeah. You just do that substitution, you get this new form. After we get this new form, by our definition of y tilde function, can we write it in the tilde version? tilde version, t tilde version, like that. Yeah. Here, yeah. The confusing part is we did a lot of substitutions, switch the symbols. Yeah, that's the harder part. Yeah, harder part. So you try to follow. Yeah. Why we can do that way? All right. Yeah. But after those steps, yeah, we get a new version of ODE. New version of the ODE for tilde function. The reason we use tilde function, we want to make the initial condition right. The format right at a 0 point. Okay? That's the main reason. Yeah. Yeah. After that, we just do the standard Laplace transform. We know how to do it. Okay? Standard Laplace transform with the basic formula. All right. So standard Laplace transform, yeah. Double prime, yeah. So those formulas, yeah. Converted to algebraic equation, yeah. All right, yeah. Just the simplification, yeah, yeah. Then find y tilde in this long expression, yeah. Long expression, yeah. But we can get that expression. Okay? Yeah, we can get that expression. So the next slide, we need to find y tilde function by inverse Laplace transform. Inverse. Okay? All right. Yeah. Oh, yeah. Our last slide today, yeah. We start from this given function. We have it. We just take inverse Laplace transform, and we do inverse Laplace transform term by term. Second, third, and the last one. We factor all the constant coefficient out. Okay, all right. Inside, yeah, we use basic formula. Okay, this one you can apply there, right? This basic formula number 7, we can apply on the third term. Number 8, we can apply on the last term. Okay? Yeah. S derivative, yeah, that as, one, yeah, if we do not use derivative, you can use the difference of the two fractions. Okay? All right. Yeah. Yeah. 1s division, you can use this formula. 1s division. But 2, if you don't like, use that twice, yeah, because twice, you can use the subtraction of two fractions. Yeah. All right. So now let's calculate this inverse Laplace transform. Yeah. Yeah. All right. Using this formula. Yeah. Without s, we can write a sign. Yeah. With s, we just take extra integral. Yeah. By that formula, with that s, yeah, we take, yeah, right. So here, yeah, we take integral, extra integral here. Okay, so we get that. Yeah. All right. Then this one, this formula, this one, yeah. So here we apply this formula another time. Yeah. Yeah. Because it's not too hard. We already have the result of the first integral. So we just apply integral another time. Yeah. So not too hard. Okay? So we just do it this way. All right. Then we can write y tilde function, yeah, term by term, using all these basic formula and these two computation results. We can write that expression. Then we simplify the expression. Yeah, we can cancel out a few terms. A few terms can be canceled out. Then we have this version. Yeah, but the y tilde function is given in little t tilde, so we need to go back to the original t variable. Yeah. Go back to the original t variable, not t tilde. Yeah. So here. So t tilde equals t minus pi over 4. Yeah. So here we just replace t tilde by t minus pi over 4. After simplification, we get this expression. Yeah. That's our solution. Yeah. Because y tilde, just a different way to write our original solution. Right? Our original y solution, in our computation, we need to use y tilde version to make the initial condition right. Yeah. Yeah, but after we get a final solution, we go back to the y function. Yeah. Yeah. So this last question, the hardest part, so many symbol switches. Yeah. So many symbol switches. So you need to understand those changes, then you're fine. Yeah. That part is relatively hard. Yeah. Try to understand that. Yeah. Changing variable. Yeah. Shifting axis. Yeah. Shifting t-axis. T-axis. Okay. Yeah. In another vertical direction. Horizontal shift. Yeah. T-axis. Yeah. All right. Yeah. That's it. Yeah. So we finished. Yeah. But still, we have Laplace transform. We're halfway here. Yeah. We just do the halfway. We have a few important topics. Yeah. We need another half. Yeah. Yeah. Because it's so important. Yeah. So yeah, we need to spend more time. Yeah. All right. So yeah, follow our plan. So I will, finish the solution file and post tomorrow morning. Yeah. So then Thursday, we do first two. Okay. At the end of class, we do first two questions.